In many situations, data analysts or researchers need to compare the results of the same individuals in two different settings or at two different times. In such situations, we often need to conduct what is called the matched pairs t-test. T-distribution can be used for multiple types of tests, including the matched pairs t-test. Many times in social science research, we need to compare two equivalent groups to assess the effectiveness of a certain intervention, or even more often, to compare the results of the same group before and after a certain intervention. In such situations, we have what is called the matched pairs design because the two groups or samples that we work with consist of either the same individuals or individuals who are very similar. With the before and after type of study, the pairs are represented by the two values that are recorded for each individual before and after a certain intervention. This is an example of paired data. We have a sample of 20 students, and for each student, we recorded the score on a pre-test, which of course preceded instruction, and the post-test, which was administered after instruction was delivered. Each pair consists of the pre-test score and the post-test score for the same student. What we're interested in here is to determine whether there is a significant improvement from pre-test to post-test. The third column in the table shows the differences for each individual between post-test and pre-test scores. The average difference for the entire sample is 10.05. But just by visually inspecting these differences, we cannot tell if they are statistically significant. In such a situation, we also have to conduct a test of significance. The null hypothesis for our test of significance is that in the population, the average difference across all individuals between post-test and pre-test is equal to 0. The notation typically used for the population difference is mu d, because we're expecting to see some growth in student achievement from pre-test to post-test. The alternative hypothesis is that the difference is in fact larger than 0. When, for a specific reason, you can expect a decrease, for instance, over the summer when students take a break from studying and might forget some of their knowledge, the alternative hypothesis should specify that the mean difference is lower than 0. Another example can be when you measure the incidence of behavior problems, you may expect a decrease after an intervention is implemented. When we have no idea whether scores should increase or decrease, the alternative hypothesis should be two-sided. The data recorded from this sample shows that the mean difference is equal to 10.05, and the standard deviation for the recorded difference is 7.56. Because we don't have the population standard deviation for this difference, we're using the t-statistic for our test of significance. If we are using statistical software or calculators, we can automatically obtain the p-value for the test statistic. When t equals 5.94, calculators or statistical software show that the p-value approaches 0. This value is obviously smaller than alpha, which is typically set at 0.05, so we can reject the null hypothesis. If we use the table of t-critical values instead of software, then we first have to find out the critical value of t. For 19 degrees of freedom and a two-sided alpha of 0.05, the critical value is 2.093. The test statistic, which is 5.94, is larger than the critical value, so we can reject the null hypothesis. In general, we refer to the results of T procedures as robust if they're not very sensitive to violations of the assumptions that they rely on. In other words, the results don't change much when these assumptions are not fully met. In general, robustness depends more on the randomness of the data than its distribution. This means that it is more important to randomly select our participants if possible, even if the data do not have a perfectly normal distribution. In general, it is preferable to obtain larger sample sizes. We should avoid using t-procedures with samples smaller than 40, especially when the data are skewed. If the data do have a symmetrical distribution, we may use it even with smaller sample sizes, but not smaller than 15. With samples of this size, it is preferable to use other procedures that do not rely on distributional assumptions, such as non-parametric procedures. In this presentation, I explained how to conduct a matched pairs t-test and how to interpret the results. Additionally, I explained the concept of robustness in relation to the t-procedures. I hope that the explanations and the examples provided were helpful.